The produce manager at mini market must order 175 pounds of apples and oranges. That's important. Each week to keep up with customer demand. Many markets' maximum budget for apples and oranges is $150. That in red there. Their maximum budget for apples and oranges is $150. Now, if the wholesale cost of apples is $90 is 90 cents per pound, and the wholesale sale cost of oranges is 60 cents per pound, which graph shows the possible solution region for the number of apples and oranges? We're looking for a solution region for the numbers of apples and oranges the produce manager can order per week. And I really should have made that line green because that's what we're looking for. So that's what our situation is. So this is a system of inequalities. So let's look at this. 100, he must order 175 pounds of apples and oranges. So do we know how many pounds of apples that he's going to order? No. So we're going to just make that X. X is the number of pounds of apples. Do we know how many oranges? No. So we'll call that Y. So how many apples and oranges does he need to order? He needs X plus Y. And he needs that to be 175. He's got to do 175. So the question is, so he can't do less than that. He's got to do 175 or more than 175. Because to keep up with customer demand, if he orders more than 175, then he's kept up. So let's say that's going to be greater than, equal to what? 175. So that's what he must order each week to keep up with customer demand. Now, how much money does he have? His maximum budget, which is the most he can spend, is $150. So we need $150. That's as much as he can spend. And so that means he's got to be less than that, but he can spend 150, so that's good. He can spend that, so we can put equal to there. So how would he be spending 150? Well, he would have to spend 90 cents for every apple. So over every pound of apple. So we need a 0.990. I'll go ahead and make it like that for every apple. Plus, he's buying oranges too. He needs 0.60. I'm just writing in financial terms for every orange, every pound of orange. So now you got two equations. Let's graph those and see what we get. If we graph those, and I'm just going to do one at a time. And let's see. There's X plus Y greater than 175. That's the first one. Then let's graph the second equation. When you graph both of them and you resize your window, zoom your window in, I zoomed mine already. It started off looking like this. And then I started hitting zoom out, zoom out, zoom out, zoom out, zoom out until I got that. So this dark area where you have the overlap represents the solution region. In other words, he can order anything in here and he'll be fine. Not only will it be less than $150, but it'll also be more than 175 pounds. So any point in here, like look at this point right here. He could, for example, he could order 200 pounds of, and since this is the y-axis, this is orange. So he could order oranges, 200 pounds of oranges, it will cost him less than 175, and it will keep up. I mean, it will cost him less than $150, and he will definitely have more than 175 pounds. Okay. Now there's no apples there, but that's okay. He still keeps up with demand. It's allowable. So, but if he wants to do apples and oranges, he can do any point that's in here, any point. So, like here, I just found a point. Like where that point is, he could do 50 pounds of apples, and he can do 150 pounds of oranges, and he'll still be under budget. So, a system of linear inequalities. I knew eventually I would get it out.